Okay, so we are going to start the morning session now, and the first talk would be on Calogero of particles and fluids. It's a 1.5 hour talk, and so please.
Thank you. I would like to thank the organizers for inviting me to this wonderful location and workshop, and you for being in attendance today. So I would like to tell you a little bit about one of the objects of my long-term fascination, the Calogero model and its various generalizations, extensions, and avatars. Well, sometimes we work on problems because they are important, but quite often we work on problems because simply they are fun. And sometimes we get lucky and we get both for the price of one. And that's exactly the case in point. The long-range one-dimensional billiards, particles on the line interacting with potentials that are long-range and keep them away from each other, also known as the Calogero particles and its various generalizations. So let's talk about it and how it all started so that we get a little bit of historical perspective. We are basically talking about a system of non-relativistic identical particles on the line, and I will set their mass equal to 1. The Hamiltonian, of course, is the kinetic term. Oops, yeah, I have to be careful here. The Hamiltonian is, of course, the kinetic term. Plus the potential term, and the potential term is a mutual two-body interaction of the inverse square type. That's the system proposed and solved by Calogero in 1969. And it is an interesting story. That's Francesco Calogero. According to what was related to me by Sasha Turbiner, Calogero was visiting ITEP in Moscow, I believe, in 1969. And it was winter, the weather was bad, he was getting a little bit depressed. And then suddenly, one day, the sun was up. And that gave him motivation to just sit down and work on something. And he figured out that if you have 3 particles interacting with an inverse square potential, you can actually solve the system quantum mechanically. So he showed it to his colleagues there, and they told him, why are you interested in this thing? This is not very interesting. Nevertheless, he persisted, and pretty soon he realized that he can solve the n-body problem, quantum mechanically also. Which was even more interesting. So he published his first paper, and very soon afterwards, himself and others also generalized it. Sutherland generalized it to the periodic model, Moser and others worked on the elliptic model, as I will talk in a moment. And also work on that was done by Olshanetsky and Perelomov on integrability, and they also wrote a seminal review in 2 parts about the classical and quantum system, which still remains one of the main references for this subject. I will not mention the names of other people in this talk because it's supposed to be a pedagogical lecture, so I don't want to keep giving references to everybody. In very few occasions I will do that. But for me it's also fascinating that the name of this model, Francesco Calogero, is an Italian physicist from Sicily, and his last name Calogero is also used as a first name in Sicily, and it's a Greek name, and it means monk. So whenever I talk about the Calogero model, I cannot help thinking about monks moving on a line, trying to avoid each other, and all that. A little bit of history about Calogero is also interesting. Calogero was the Secretary General of the Pugwash Conferences on Science and World Affairs organization between 1989 and 1997. And that organization received the Nobel Prize in 1995. So we could say that in some sense, Calogero is a Nobel Prize winner because he was the chair when the Secretary General when the Nobel Prize was awarded. If you don't know about this organization, other than the fact that they won the Nobel Prize, it was founded by Bertrand Russell, CCNY, that's my affiliation, City College of New York, ex-professor. Ex means expelled professor. He was actually expelled because of political reasons. Those were the days. A whole lot of other eminent people became the Secretary General. You can see a few of them. No. Calogero did not receive the Nobel Prize for his model. Calogero was the Secretary General of Pugwash Conferences on Science and World Affairs Organization when that organization received the Peace Nobel Prize in 1995. So to the extent that, I don't know, Carlo Rubbia, or for a more recent example, that Barry Barish received the Nobel Prize for being the administrator of LIGO, even though the actual observation happened when he was not the chair, and yet he received the Nobel Prize, I would say maybe Calogero deserves to be called the Nobel Prize winner. Are you recording any of that? I hope not. Yes. He did? Bertrand Russell? All right. Thanks. Next time, if I ever give this talk again, next time I will put it there and I will reference you for that. Verbally, yes. Right. Okay. Point is that that Calogero has other activities other than the model. I don't think that he has worked on his model for the last several years or decades, but that was an interesting bit, I hope an interesting bit of history. So let's give a physical look to that system. Let's see what is so special about it. Of course, as we said, it's a system of identical particles. All of them have the same mass, and their interaction is permutation invariant. And their interaction is of the inverse square potential type, unlike Coulomb, not forces, but potential. That interaction is special for various reasons. First of all, you can think of it as a kind of mutual centrifugal potential between particles. That's the form of the centrifugal potential in any number of dimensions, actually. But this centrifugal, in quotation marks, potential is between any two pairs of particles. Also, it is the borderline short distance behavior of the potential between having or not having instabilities of particles being sucked into each other. It's a classical problem that you give, I guess, to your students in mechanics, that if particles interact with a power law potential, negative power law, if that power is less than -2, if the potential is stronger than 1 over x squared, the particles will always get sucked into each other. If it's less or equal to 1 over x squared, the particles will not get sucked into each other when they move in 2 or more dimensions. It's also the borderline long-distance potential for phase transitions in 1 dimension. If the potential falls off like 1 over r squared or faster, then there is no phase transition and you get a gas. If it falls off slower than 1 over x squared, like say 1 over x or any other power, then at some finite temperature, you get a phase transition from a gaseous phase to a crystalline phase. And 1 over x squared is right in the middle. You can say that there is a phase transition at 0 temperature. Also, all these properties stem essentially from the fact that it is a scale-free. Wow. Okay, there we are. That it is a scale-free potential. P squared, of course, has units of 1 over x squared if we put h bar to 1, which we shall do from now on. So the potential has the same dimension, scale dimension as the kinetic term, and therefore the Hamiltonian is scale invariant. The coupling constant of that potential in units where h bar is 1 is a pure number. That's again unique to this potential. And of course, this coupling constant should be positive so that the particles repel and they are stable. If it's negative, the particles would fall into each other. They are on the line, so they have no room to escape. And as we will argue, quantum mechanics improves things a little bit, allows for a slightly negative value of that potential. That's the sort of, sometimes I call it the plain vanilla Calogero model. But you can do things once you have this model. First of all, you can confine the particles. Yes. Okay. So you can confine the particles in a box. And that box could be either a harmonic trap, which is exactly what Calogero did after he solved the completely scattering problem. And it is also a special system. Or you can imagine of putting the particles in a periodic box. And the way that you do that is you say that the coordinate x is periodic, so the system basically is infinitely many copies of the particles in the fundamental domain from 0 to L. L is the periodicity. So that means that each particle interacts with each other particle not only through the distance within the domain, but also through the images of this other particle. So the interaction of a particle with the other particles will be the sum of n equals 0, the particle in the domain, plus all the images. And that summation can be done explicitly, and it gives you 1 over sine square of the distance in proper units. That system exactly was solved, examined, and proposed, examined, and solved by Sutherland, and we call it the Sutherland model. And it's interesting, it's kind of a coincidence, if you wish, about this potential, that this is the same result as you would get if you simply said that the particles interact through their chord length, if indeed they are moving on a geometric circle on the plane, which is something that Sasha mentioned, I believe, yesterday. We can do more things. We can take that periodicity L and analytically continue to an imaginary value. The potential remains real. Yet the system remains as solvable as it was before. It's just an analytic continuation of the solutions. And that is the hyperbolic model, where the interactions are now of the inverse sinh hyperbolic sine square. So although they still have the same 1 over r square behavior at coincidence, near coincidence points, they fall off exponentially. So the behavior of that system is quite different than the previous one. And once you have that, you say, gee, I would like to periodize it too in X. Now it's not periodic anymore because L became imaginary. And once you do that, you end up summing over infinitely many copies of that, and that gives you the Weierstrass elliptic function. And that model, which depends on 2 parameters, L, the real periodicity, and L prime, the periodicity in the imaginary domain, if you wish, is the most general type of 2-body potential that you have within this Calogero family of models. It contains everything else as a limit. Take this L or L prime to go to infinity and you recover the various other limits. However, it's also one of the most challenging models to solve. Very little is known explicitly about it, either classically or quantum mechanically. And in these lectures, we will give it rather short shrift. Okay, I told you why this system is kind of special, properties of 1 over r squared, but why is it interesting? Because it tends, other than the fact that it has all these interesting properties, it tends to pop up in various situations which are themselves of various interests. It's kind of a jack-in-the-box. You open a problem and out pops the Calogero model in one guise or another. Here are a few of its applications. It is an effective description of fractional quantum Hall states. If you have a quantum Hall droplet, as they call it sometimes, the boundary states in that droplet can be described as particles of a Calogero system. I will say a little bit more about that in my research talk, but it's just the fact. And the filling fraction of that bubble becomes essentially the inverse of the Calogero interaction. Another application is in spin chains in macromolecules. If you have molecules that interact not just through their spins interact not just through nearest neighbors, but next to nearest and next, a good approximation would be to say that their interaction falls off as the square of their distance. It's just an approximation. And once that happens, this spin chain is also part of the Calogero family and can be solved. And it's another application. One of the first applications of the Calogero model came actually in fluid mechanics, which is appropriate, I guess, for the topic of this conference. It is actually in the one-dimensional motion in the interface of stratified fluids. So imagine that you have a trough, long trough, filled with 2 non-mixing fluids, could be water and oil. The interface between these fluids, if the deviations are one-dimensional, will propagate. And it propagates according to this equation, which is usually referred to as the Benjamin-Ono equation. I don't know why, because Benjamin first proposed it in 1967. Almost simultaneously, Davis and Akrivos did a lot of work, re-derived it and did a lot of work on it. And then almost 10 years later, Ono added something, but it's still called the Benjamin-Ono model. You tell me why. Notice that this is an equation for this deviation u from the flat interface. This equation in time and space x is both non-linear because of this term and non-local because of that term, where this is the Hilbert transform. So in principle, it's very hard to solve, and nevertheless, it is solvable, and it has soliton solutions. Solitons, that means, as you know, configurations that keep their shape, move at a constant speed, keep their shape, and when they collide, they re-emerge with their shape unscathed. And the center of the solitons has an equation of motion which is exactly the same as that of Calogero particles. So solitons are, their guiding centers are Calogero particles. There are many other applications. They appear whenever you have a matrix model, you should expect a Calogero model, and matrix models have been used for descriptions of quantum gravity, string theory, etc. They also appear in two-dimensional gauge field theory, etc., etc. So if the droplet is circular, then the excitations live in a periodic space, so that would actually be the Sutherland model. Right. If you have a droplet that is half a filled plane, then it would be just a Calogero model. The interface would be just a line. Let's talk a little bit about the stability and the hermiticity properties of this model. As I mentioned before, classically, G should be positive to ensure stability, otherwise particles would be attracted and sucked into each other. Quantum mechanically, the uncertainty principle improves things, because the zero-point motion tells us that particles cannot actually go into each other, so it is a balance between minimizing the kinetic energy, which increases as they come closer, and minimizing the potential energy, which increases as they go far apart. And because they both scale the same way, it all depends on the coupling constant. And it turns out that if the coupling constant is negative, but no more negative than -1/4, the system is still stable. Actually, this is an exercise in Aldau and Lifshitz. I invite you to repeat the exercise, regularize this 1/x² potential any way that you wish, cut it off like that, then solve the problem and see what happens as you take the limit of the regulator to 0. Because of this, it is convenient to parameterize. What am I doing here? I have trouble with this. It is convenient to parameterize the coupling constant in the form L times L minus 1. This is something that automatically, it's a quadratic form that automatically will give you that as the minimal value as long as L is real. So it's convenient so far only because of this, but you will see soon that it's convenient for other reasons. I should warn you that people like weird stuff. So the model with G less than -1/4 has been examined, and it can be made to have a Hermitian extension. So there are ways to make sense of the model for even more negative G, but these are rather contrived, and for everything that we'll say and for everything that has to do with physical applications, these values are relevant. Notice, however, that there are two values, L and L price equal 1 minus L, that give the same coupling constant. You may say that's irrelevant because this L was just a way to parameterize it. Actually, if you examine to see how the wave functions of such particles behave, at coincidence points, they behave as x to the L, where x is their distance. So again, the question is, which of the two L's? We see something similar when we solved the problem of particles in a central potential and we examined the behavior of the wave function at the origin. There we have two types of Bessel function and we keep one for normalization. Similarly here, it's just that when the interaction is positive, then one of these L's will be positive, the other one will be negative, and we only keep the positive one. However, when the interaction is between 0 and -1/4 in this quantum mechanically allowed negative region, both L and L prime are real, so you you wouldn't know which one to keep. And it turns out that you can keep either, and the two systems are two different quantum mechanical realizations of the same potential. So both are acceptable and they are inequivalent. And it's useful to keep them both because, for instance, when G equals 0, L equals 0, and L equals 1 have different properties. They correspond to fermions or bosons. So it's useful to keep them both. And also point out that if we were to reinstate for a moment H bar, the expression G equal L times L minus 1 would become G equals L times L minus H bar, just to point out that this form, this minus 1 here, will be a quantum correction when I justify this form of the interaction strength. Now, what about statistics? You may have heard the statement that Calogero particles somehow correspond to particles of fractional statistics. What about the real statistics of the particles? Does it matter if you quantize the system as a system of fermions or bosons? Actually, it doesn't, because the 1 over x squared potential is quantum mechanically impenetrable. That means the scattering amplitude of a particle going through an 1 over x squared barrier is 0. That means that if you start with particles with their positions in a particular ordering, they can never go through each other, even quantum mechanically. And therefore, if they can never go through each other, what happens in these other sectors, these other permutations, is irrelevant. That is to say that ordinary statistics is irrelevant in this problem. And that has caused some confusion in the literature. You see sometimes papers that claim different results, but it's never the case. You could, for instance, decide to start with a wave function that lives, is non-zero, only in one wedge of this r to the n space, in one ordering of the coordinates, and that wave function will stay there. It will never go anywhere else, and that's your full quantum mechanics. So all physical observables of the system are independent of the true, in quotes, statistics of the particles, and any statistical properties that the system has are controlled and subsumed in the strength of this interaction L. In particular, L equals 0, as I mentioned, and L equals 1 correspond to free bosons and free fermions. The properties of the system are identical to free bosons and free fermions. Other values, it's natural to call them generalized statistics, fractional if it's between 0 and 1, or extended beyond fermions, but we will talk about that in some detail. Of course, what this makes system both interesting and relevant for this conference is integrability. This system is integrable. A classical Hamiltonian system is called integrable if it contains as many conserved quantities in involution, Poisson commuting, as there are degrees of freedom. These quantities should also be time independent, otherwise it becomes a triviality. You can always choose the initial values of the positions and call them integrals of motion, but that's not useful. And such quantities do actually exist for this model. If you have two particles, of course, it's trivially integrable because in the absence of external potentials, the total momentum and the total energy are conserved and they commute in Poisson sense, but there are other quantities when n is greater than 2. So let's talk about this a little bit. The first real math that you're going to see today. The integrability is proved through the Lux pair. We consider, at this point without motivation, although you will see where they arise in a moment, we consider these two Hermitian n by n matrices. N is the number of particles. One matrix has a diagonal, which is the momenta, which will be the momenta of the particles in some off-diagonal terms of this form. And the other matrix is a little bit more peculiar. It has 1 over x squared terms like that. Now, we can use the equations of motions of the Calogero particles, assuming that P and X are positions and momenta of particles obeying Calogero dynamics, to deduce the time evolution of these two functions, in particular of L. And you do it, it's some algebra, but easily doable, and you discover that the time derivative of that matrix is the commutator of that matrix with the other matrix. That tells you that the evolution of L is through unitary conjugation. The evolution through an infinitesimal time step is through this unitary operator, and the finite evolution is through a big unitary operator that's actually the path or the time-ordered exponential of this field A. So this A is like a gauge field in time in one dimension, and this would be like a gauge transformation. This tells us that the eigenvalues of this matrix remain constant in time because a unitary transformation does not change the eigenvalues. So either the eigenvalues, or better yet, all the traces of all the powers of that matrix will be constants of the motion. And these are our integrals. The fact that they are also in involution requires a little bit more work, but it can also be shown. So that is interesting because it tells us already quite a bit about the properties of the classical system. We consider again particles with Calogero dynamics without any external potential, so there can only be scattering states, both classically and quantum mechanically. As time goes to either plus infinity or minus infinity, the particles will eventually fly away from each other, their interactions will fall off to zero, so they will move freely with some asymptotic momenta. The integrals of motion, however, are constant no matter where the particles are. Therefore, in that case, these integrals of motion, if you look at the form of that matrix, these x's will go to infinity. This matrix becomes diagonal, containing just the momenta. So these integrals of motions just become the sum of powers of the asymptotic momenta. Therefore, the asymptotic momenta must be conserved. Because if you have the sum of all the powers of these momenta being the same both before the particles interact and after they interact, the only possibility to have these quantities equal is that these actual momenta are equal up to a permutation, because these are permutation invariant quantities. Some more work also reveals that the corresponding angle variables to these integrals of motion asymptotically become G-independent functions, which means that not only do the particles scatter without, eventually, many body scattering, they scatter without changing their asymptotic momenta, but also their impact parameters are not changed. So they evolved like that, and they deviate from that only in the region where they interact strongly, and when they resume their almost free motion, they go back to this asymptote. For two particles, this is almost obvious, because a shift like that would be a dimensionful parameter, would have the dimensions of length. However, there are no dimensionful parameters in the problem. The coupling constant is dimensionless, so there you expect it, but for more than two particles, it's a non-trivial fact. There you do have other possibilities because of the ratios between particle coordinates. And this gives us this following space-time picture of how the system scatters. So consider that we have three particles. This is space and time. At large negative time, the particles are simply coming asymptotically from infinity, and they converge so that they could scatter, so they move along these asymptotes. When they come near each other, they interact, so they start steering away from their asymptotic paths. But lo and behold, after they are done interacting, they nicely resume exactly the same asymptotic trajectories that they would have if they had not interacted. The only thing is that particle 1 has now assumed the path of particle 3, that of particle 1, and particle 2 in this particular case comes back to itself. So, if you did not look closely at what happens at the interaction, if somebody told you only, here's a system of particles, that's how they scatter, here's how they come in, here's how they come out, you would say, gee, this system looks to me free. There is, however, a suggestive fact. If you calculate the total action of this process, start from some big negative time to some big positive time, time around zero being the time that they interact, and you calculate the total action of that system according to the standard Lagrangian, kinetic minus potential energy, that action will be the same as the corresponding action of the free system with the same initial conditions, plus a constant. And that constant is proportional to the square root of g times pi times the number of 2-point crossings here, there, and there that these particles would need to undergo if they were free. So you have that much extra contribution in the action for every two-particle exchange. Why is this suggestive? Yes. Yeah, in one dimension, of course, particles have to bump if they can go through each other. So what I call impact parameter is this. If asymptotically, as they come in, they have paths, their paths will be, of course, their momentum times t plus a. So it's the parallel shift, if you wish, of these lines that I drew. That, perhaps slightly abusing language, I call it an impact parameter, because it tells you that at time t equals 0, that's where this particle would hit the real line. That's all. Okay. If you don't like the word impact parameter, erase it from your memory. This is what I mean. I mean, these lines, their slope is determined by the asymptotic momentum, but they could be parallel transported, and where they cross the real line, I call the impact parameter. That's all. And that is preserved, because in principle, they could re-emerge with the same momentum, but at a later time, they would suffer a time delay. Well, here, that doesn't happen. The real particles or the free particles that mimic their motion? Because the real particles never cross. They do what these red lines do. They come close to each other, they repel each other because of the interaction, so they move in these curves, but eventually, after they fly away from each other, they nicely and exactly resume the exact same paths that they would have if they were free. That's what I wanted to convey. Is this still unclear? All right. Okay, now let's move a little bit to the quantum system. All this is kind of a grand introduction to the properties of this system so that you see what is nice and interesting about it before we go into more details. Again, we will parameterize now this interaction in the way that I told you before, briefly reintroducing H, but we will take it to 1. This is just to show you that the classical limit corresponds to taking L to infinity. It's H times L that remains constant. So if you take H bar to 0, L should go to infinity. And the Lux pair formulation that I showed you before goes through quantum mechanically. If you start with the exact same thing, now these matrices are operator matrices because their elements are quantum mechanical operators. You can repeat everything, and basically everything works in exactly the same way, so you can show integrability. And once you examine the system a little bit closer, you see that the scattering phase shift that you now have when you have particles coming in as plane waves and scattering and emerging again as plane waves, the scattering phase shift is a constant. That means it does not depend on their momenta. It just depends, it just depends on the number of particles. So this is again the number of two-particle crossings that you would have times pi L. And L in some sense is the square root of G in the classical image. So you see now the classical quantum correspondence, the action became phase. This is interesting because, as you remember, the derivative of the scattering phase shift with respect to each scattering momentum gives you the corresponding shift in what I call impact parameter, perhaps by abuse of notation. Actually, the derivative with respect to the asymptotic energy of each particle would give you the time delay of this particle in the interaction. Those time delays are all 0 because this is just a constant. So you get the quantum analog of what we saw before. Particles scatter, and you wouldn't know that they interacted by looking at their asymptotic data. There is nothing to show you that they interacted. So these Calogero particles scatter exactly as if they were free. The only thing is that their scattering phase shift is now dependent on their number and also on this coupling constant G, or equivalently L. Now, if the scattering phase shift were 0, that would be exactly the scattering of free bosons. If this scattering phase shift were pi for each particle exchange, so L equal 1 here, that would be exactly the scattering phase shift of free fermions. Well, this tells you that the scattering phase shift is pi times L for each two-body exchange, so you can interpret these particles as particles obeying exchange statistics of order L. So this is the first sense in which you can say that these particles are free or almost free, but with fractional statistics. It is interesting to examine the quantum mechanical properties of the periodic model. In the periodic model, the particles move on the line. If the particles were free, they would just have their kinetic energy and the momenta would be quantized, so they would be quantized on a lattice. And if you take L to be 2 pi, they would be quantized to integers. And if the particles were indistinguishable, then you can put as many of these in the same momentum if they are bosons, or if they are fermions. Of course, you have to distribute them at different states. We are always talking about spinless fermions, non-relativistic spinless fermions in one dimension. So that's what you would have for free bosons and free fermions. This is what happens with the Calogero model. You can show, we will see, that the spectrum has this form. It can still be characterized by a set of integers, pi. These pi's are integers and they obey this rule. They are ordered integers. But there is this extra interaction term and a constant. This constant is not very interesting, but notice that for L equal 1, it becomes the ground state of n free fermions, ground state energy of n free fermions. But this interaction energy is interesting because it tells us that this spectrum seems to be different than the standard one. However, with a small redefinition of P, define some new P bar that we call usually pseudo-momentum to be P plus something proportional to the order of the particle. In terms of these new P's, the energy simply becomes the sum of the squares. So in terms of these momenta, the energy becomes the same as the energy of free particles. The only thing now is that now these pseudo-momenta do not obey this bosonic exclusion, if you wish, rule, but they obey this generalized rule. It tells you that they have to differ, so they are like fermionic, but they have to differ by L as opposed to 1, which could be the case for fermions. As for fermions, they would need to be at different lattice points in momentum. And that's the sense in which these Calogero particles have fractional exclusion statistics. Statistics not in the scattering sense, but in the statistical mechanical sense. And this concept was introduced by Haldane, not for Calogero particles, but for the corresponding spin chain, but it works for all these systems. The ground state of this system forms what we could call a pseudo-Fermi. Assume for simplicity of pictures that L is integer and equal to 2. So the ground state is you put all the particles in as low a momentum as possible, so around 0, but their mutual momenta have to differ by at least 2. So if you put one at 0, the other one has to be at 2, minus 2, 4, minus 4, etc. So they fill, n of them would fill the space, but with a gap of 2. And we could call that a pseudo-Fermi. It turns out that this is actually a Latinger liquid that they form. But let's stay with this picture for a moment. This is, of course, the ground state, and over that ground state, you can have excitations. And just as in a Fermi you can have particle and Hall excitations, you can also have particle and Hall excitations here. A particle excitation, of course, would be to take this particle and move it up this lattice, or take this particle and move it up this lattice. That's clearly a particle moving away from this pseudo-Fermi. But we can also have Halls. You would say, okay, Halls would be take one particle and remove it. That would be one Hall. Actually, not quite, because although that would be the absence of a particle, it is not the most fundamental excitation that you can have inside this pseudo-Fermi. Let's see what happens. So I took one particle here and I removed it, I put it over there, and I created a hole, or rather a gap of one particle. I can now take this particle and move it by one place. This is a local motion within the pseudo-Fermi. So now I created two gaps, each one of them not of 1, 2, 3, 4, as it was here, but of 3, a gap of 3. And if I move this particle even further, these two gaps can be moved away from each other. So you see that by removing one particle, I have effectively created two elementary excitations that correspond to an absence of particle, a hole, and these two can be now moved independently. So we see that one particle corresponds to two holes. That hole is the minimal one, because if you were to close it any further, you would go to the ground state. So you see that in this case, for L equal 2, one particle corresponds to two holes, and that generalizes easily. You can play this game with a gap of 3 in the ground state, and you see that each particle, the absence of a particle creates L holes. So we see that there is a kind of peculiar, non-trivial duality between particles and holes that generalizes the duality in a fermionic system. The particles have the following properties. When they come together, they pack, that means that they fill the momentum space, in units of L. They require a space of L so that they can sit together. But when they are excited, they can excite it by 1 unit. Once you take a particle and put it here, you can excite it 1 by 1. On the other hand, holes pack, they take up only one space, and that may look paradoxical because you say, but they look big to me. They may look big, but when you put them together, they each take up only one space, because if you increase this gap by 1 unit, you create an extra hole. Another unit, you create an extra hole, and so on and so forth. You can see it again by these local changes. So although they look fat, they are actually occupying only 1 unit when they pack, but when they are excited, they can only be excited by L units. Let's see how is that from this picture. Let's say that you have this hole and you want to excite it. How do you excite it? You want to move it to the right. You cannot move this particle to the right because the Fermi sea is filled here, so you would need to move this particle to the right. That you cannot do either. So you move this over there and that over there, and you see that this hole has moved by 2 units. Or, to say it better, if you move this particle by 1 unit less, there is no hole here because the gap is 2, the same as in the vacuum, but you created a hole here. So by moving a particle by 1 position, you move the hole from this place to that place. You move the hole by 2. So holes, as they move, they are excited, their momentum is excited in units of 2, or in general in units of L. So they have this kind of peculiar statistical versus excitation properties that are mirror image of each other. That actually generalizes in a more formal sense. Their correspondence is that you have 1 particle corresponding to 12 holes. There is a particle-hole duality, but that also involves an inversion of that coupling constant, because if you invert that coupling constant and you also rescale the momenta, these properties are mapped to each other. In the continuum limit, many particles, and you could also take the classical limit, the particles that we describe here will behave like solitons, and we will talk about that quite a bit, I guess, in the last lecture, while holes became finite small amplitude waves, and the two are dual descriptions of the system. Okay, that was kind of a not actually so brief review of the properties of this system. Yes? When L is an integer, it makes the pictures look simpler. If it's not an integer, you can still do it, and it works in exactly the same way, but it's not so easy to have an integer lattice. You have to start with a ground state where their distance is a fraction, but then remember that every time that you try to move each one of those particles, you have to move them by an integer, because individual particles move by integers. So you can do exactly the same thing for fractional L. It's just not so convenient to draw these pictures that I did. Okay, that completes our kind of review of the model. So before I go full steam into examining mathematically the properties of this model, I would like to derive it in quotation marks, starting from the concept of particle statistics to see why statistics is very relevant for such systems. So assume that you have a set of indistinguishable particles, and here I would like to stress the distinction between identical and indistinguishable. Particles are identical if they have exactly the same properties, but in principle, if you could take one of those particles, paint it red, and throw it among the remaining particles, you could tell which particle it is. If, however, this is not a physically possible operation, you call the particles indistinguishable. So, indistinguishable particles are identical particles where all the physical operators that you have, the Hamiltonian, and all possible perturbations of the Hamiltonian, or all measurements that you can do, are invariant under particle permutation, which means that you cannot paint individual particles, you can never tell them apart. That means that this group of permutations becomes almost like a gauge symmetry. The way that we deal with that in field theory, and we believe that the world is described actually by field theory, is to say that particles are field quanta or irreducible representations of the Poincaré group, and therefore they are a priori indistinguishable. When you say that they have two quanta, you don't say which one came first. They both exist there. In the many-body first quantized point of view, and also in the condensed matter point of view, that you actually have particles moving in a body, etc., we consider the particles as being the fundamental degrees of freedom. But for identical and indistinguishable particles, the permutation group of the particles is a symmetry of, as I mentioned, of both the Hamiltonian and all physical observables. Such symmetries are called, as you know, gauge symmetries. A gauge symmetry is a non-physical symmetry, a symmetry that does something that does not produce a physical change to the system, and relabeling the particles is exactly one of those. And therefore, you should really quantize that as a gauge symmetry. That tells you immediately that all irreducible representations of that symmetry are superselection sectors. If you start with such a representation, you can never move physically with another representation. No Hamiltonian or conceivable perturbation will do that. And different representations essentially correspond to independent quantum systems. So when you quantize such systems, you can do it in two ways. You either reduce the system to a set of gauge-invariant observables, that means you eliminate the gauge freedom, or when that's not possible or not desirable for some reason, you realize the gauge symmetry as a symmetry in the Hilbert space. You impose Gauss law, so to speak, on the states on the Hilbert space, and that ensures that all quantum mechanical matrix elements of gauge-invariant observables will actually be invariant under gauge transformations. In this latter case, you also have the option to augment the system and its gauge symmetry. And as long as the gauge-invariant content remains the same, you say that if I augment my gauge symmetry, I didn't do anything physical to the system. This is dangerous because when you put more symmetry into the system, more gauge symmetry, you may run into anomalies, but we will see how this will manifest in the Calogero model. So I will explain how you can do these two things in the context of the Calogero model. First, reducing to gauge-invariant observables. What are the gauge-invariant observables of identical particles? They are, of course, all possible functions, in quotation marks, that you can write of the fundamental coordinates and momenta of the particles that are fully permutation invariant. And one complete basis of such functions are these quantities here. They are powers of the coordinates and the momenta of the particle, summed over all particles so that they become permutation invariant. And this means normal ordering. Remember, these are now quantum operators, so you should order them in a particular way. And it's convenient usually to take Weil ordering. You fully symmetrize this product because, first of all, this makes it a little bit nicer in properties, and second, it makes it Hermitian, while as it is written without normal ordering, it wouldn't be Hermitian. In general, however, this set is overcomplete. Not only you have a finite number of particles, capital N, but in principle, these indices could go all the way to infinity. Even if you were to truncate this to capital N, so that you at least have all the coordinates included, this set of N times N plus 1 over 2 quantities that you would get in this case is still overcomplete, or N square actually, if I let both indices run from 1 to N, is still overcomplete. N square observables for 2N independent operators. This overcompleteness arises classically in the fact that there are identities between these quantities, and quantum mechanically to the fact that there are Casimirs in the algebras of these I's. That means there are combinations of these I's, that commute with all the i's, and therefore they can be put equal to constants, which is classically the statement that this corresponding combination is 0 or has some other value. This algebra, of course, many of you would have already recognized. If you parameterize these quantities appropriately, this is like pretending that these are part of an exponential, so you do this summation here with this momenta trying to exponentiate it. So instead of I, mn, you define this I of these continuous variables k and q, that would be like momenta. The Poisson bracket, or the commutator actually, quantum mechanical commutator, not Poisson bracket, commutator of those quantities I is the famous sign algebra. The corresponding commutation relations of these i's has this form plus corrections, and I have put h bar to 0. These corrections mean simply lower order terms in these indices m and n, and you may recognize this as the W infinity algebra if you have seen that before. So this is the classical W infinity algebra, classical meaning that we have put no explicit central extensions, etc. And for finite n, this algebra becomes nonlinear Wn algebra due to the identities, but we could actually keep the full tower of I and m and impose these identities as relations for the Casimirs of the algebra. Now, each value for these Casimirs will define a different quantum system, and therefore you start with the same quantum system and particles, no matter what the interaction, and their quantization can be done in various ways according to these Casimirs. So you have to assume that these are alternatives that you have for particles, and what do you have about particles that are identical and indistinguishable that would make them inequivalent? Only their statistics, bosons or fermions. So the values of these Casimirs would correspond to quantizing these particles as different statistics of particles. To see how this works in the simplest case, consider the special case n equal 2. There the center of mass and coordinate and momentum are clearly one of these two quantities. They are permutation invariant. Their relative coordinate and momentum are not gauge invariant, but you can define their squares and their product like that. X is now the relative and P is the coordinate and P is the relative momentum. So these are clearly now permutation invariant. And the algebra of these three quantities, A, B, C, and the previous ones, that's how they are related, closes. The center of mass, of course, commute among themselves, but the relative quantities A, B, C form this algebra. And this is the SL2R algebra. Classically, these three variables obey this constraint. You see it from here immediately, if this is just XP. Quantum mechanically, it means that there is a Casimir that would be the classical value of this variable, and this is the usual SL2R Casimir, similar to the SU2 Casimir. It's just that now this Casimir does not need to be 0. This Casimir can actually take any value, and standard representation theory of this algebra, if you want it to be unitary, tells you that this Casimir can take any value. It doesn't have to be quantized. This is a non-compact group, but it has to be, lo and behold, bigger than -1/4. That's suggestive. This -1/4 tells you that this is reminiscent of the Calogero model. In fact, you can parameterize this Casimir this way, and it tells you that the properties of the quantum system are determined by what value you choose here. You can realize these operators A, B, C in terms of three, so to speak, fundamental variables x and p like this. If you represent A as x squared, B as xp plus px, and C as p squared plus that, then the algebra of these three operators is exactly the SL2 algebra that we wrote here. But the value of this Casimir, if you do AC plus CA minus P, is exactly this number. So what is this? This is the three observables of an identical system where what was before P squared, that would correspond to the kinetic energy, the relative kinetic energy of this system, has now become P squared plus a Calogero term. That means that the Hamiltonian that corresponds to this system, if you quantize them with this particular value of the Casimir, is actually the Calogero Hamiltonian. So the Calogero model can be thought of as free, in quotation mark, particles, free meaning that the Hamiltonian corresponds to this particular element of their algebra of observables, exactly the same element, but at a different representation of this algebra with Casimir non-zero. So in that sense, statistics are here. Well, for n equal 2, similar things happen, no reason to dwell in it. If G is less than 0, there are two inequivalent representations of, although the Casimir has the same value, it corresponds to two inequivalent representations of SL to R. So everything works exactly as I told you before. For G equals 0, you have two of those inequivalent representations corresponding to Bose or Fermi. And so we end up with a grand idea that statistics corresponding to superselection sectors of the system in terms of their permutation group is directly related to Calogero dynamics. Yes. C was, if you remember, just p squared, where p was the relative momentum of the particles. And then I said, but I don't like the relative momentum because it's not a gauge-invariant quantity. I like p squared because it is, so I like these ABCs. I keep these ABCs and they obey this algebra. So that's all I know now. And to say that the part of the system is free means that my Hamiltonian is actually C plus perhaps p squared, the center of mass. Okay? That would correspond to a free Hamiltonian. So I always have my Hamiltonian to be a fixed element of this group of observables. Because then it would be a trivial Hamiltonian. A Casimir tells that it's a constant for all states of the physical system. You don't want your Hamiltonian to be a Casimir. It's a Casimir of all physical observables, not a Casimir of a subgroup of something. So Casimirs are uninteresting things that you fix them to a value and forget them. They are super selected. So I call this a free Hamiltonian if it is what you would call a free Hamiltonian for particles, just the sum of the square of their momenta, I2 basically, I2, 0. And that free Hamiltonian still can be quantized in various ways because this Casimir here can assume different values. And if you quantize this algebra with the Casimir being non-zero and equal to that number, you end up realizing the Hamiltonian in terms of these operators. It is like a spin, but with the only difference that it would be a spin if the group were SU2, but here it's SL2, so it's non-compact and can range from from 0 to infinity. Yeah, yeah. There it is. Yeah? There. Yes. No, no. What I did, indeed, what I did was the following. I have these three operators, A, B, C, disregard these expressions, and I say, now I have these three operators and the corresponding two for the center of mass, and all the higher ones, and I quantize the algebra of those operators. And the way I did it, I recover a representation with states, etc. That's my quantum system. How can I think of this quantum system? I can think of this quantum system by giving an explicit realization, representation in terms of wave functions, if you wish, of these operators, in terms of a coordinate x and the corresponding canonical variable p. But to realize this algebra in a way that the Casimir will come out right, if you do AC plus CA minus 2b, effectively, you see that the realization must contain this extra term. This is required to get the correct Casimir. So you say, either you quantize this algebra and you never talk about wave functions and it gives you all your states, or you talk about the wave functions of that realization. It's equivalent. But this is just a Calogero model. That's all. Okay. So that kind of gives you the idea that Calogero model has a deeper connection with statistics than any kind of heuristics about scatterings and maybe exclusions, etc. But let's now go to the second way of realizing a gauge system that will take us to a real piece of math that you can do about the Calogero model and derived stuff, which is augmenting this symmetry as a matrix model. The standard approach, of course, would be to just stick with the original xi and pi, and then decompose the states in terms of representations of the permutation group. But you can do something else, a kind of different approach. You start with an augmented system, more degrees of freedom, that has a gauge symmetry that when the system is reduced without gauge symmetry, it leads back to the same identical system of particles. And the way that we will do it is that we will formulate particle coordinates as the eigenvalues of an n by n Hermitian matrix. So that's the motivation for going to the matrix model, if you wish. A priori, when you diagonalize a matrix, there's no specific ordering of the eigenvalues. So if you just proclaim your particles to be the eigenvalues of that matrix, you made them identical because there is no ordering. You also made them indistinguishable if you claim that the diagonalization of this matrix is a gauge symmetry. So you promote the unitary conjugations of that matrix that you will consider into a gauge symmetry, and lo and behold, now you have a gauge system whose quantization is going to give you identical and indistinguishable particles. These states now will be related through irreducible representations of that conjugation symmetry, and all these all the conjugations within the same irreducible class will correspond to a unique physical state. So let's do it. This is, for those of you who are interested to see just the nuts and bolts, these are the first real nuts and bolts that you see. We start with a Hermitian n by n matrix. We will call it M for matrix. And we will take the Lagrangian to be exactly the same as it would be, would be the Lagrangian of a free particle with coordinate M. It's just that now the coordinate is a matrix. So it's a kinetic term minus a potential term, V of M, some scalar function of M, some function that when you expand it, it has scalar coefficients, but the variable is this matrix M. And of course, to get a scalar out of all that, you need to trace it. Well, clearly this has time translation as an invariance, and that leads to a conserved quantity viewed as a Lagrangian system, which is the Hamiltonian, is the energy, kinetic plus potential, exactly the same as in a free particle. But it is also invariant under time-independent conjugations of that matrix, because if you conjugate that matrix M, and given that this potential is a scalar potential, the conjugation matrices will come on either side, and the trace will be invariant. So that transformation leads to some conserved quantities that have to be matrices, because U is a matrix, so the generators have to be a matrix, and that is a form of angular momentum. It's the usual matrix commutator of M and M dot, the matrix and its momentum, times I, so that it be Hermitian. You can think of these J's, since they are the generators of this transformation, as gauge charges in our visualization of that group as a gauge group, and that will determine the realizations of the system and the statistics. But we will not worry about that. We will first deal with the classical system. So we would like to solve this model and see to what it corresponds, given the fact that our I is on its eigenvalues. We need to look at the dynamics of the eigenvalues. What do we do? Well, we parameterize this matrix in terms of a diagonal matrix containing the eigenvalues plus the diagonalizing matrix U, which is unitary and it's in general time-dependent. This conserved matrix J, then, is the angular momentum that moves that U, and it's useful to define that matrix minus U minus 1 U dot for later convenience. It's kind of like a gauge potential. Then you simply rewrite the Lagrangian in terms of the variables lambda and U. M dot is easily calculated to be like that, and is U times some matrix L U minus 1. J, the conserved angular momentum, turns out to be like that, and it's again U times some matrix K u minus 1. And L, the Lagrangian, which is m dot square plus p of m, takes this value. So this comes from the kinetic term, is what happens when you square that term. And this is the potential term that is already dependent only on the eigenvalues. And this can be written in terms of matrix elements. Remember, lambda is diagonal. So in that cases where lambda is diagonal, this becomes the sum of x dot square plus this term. And here I see that I have forgotten to write minus sum of v of lambda. Oops, which way did I go? There. So here there should be an extra term because of the potential. All this is actually a kinetic term. Well, the matrix elements of A and K are related. Remember, K is essentially the conserved J in a different basis. K is time dependent because, in general, because U is time dependent. But in the kinetic term, these A's appear, which is this matrix. But A and K are related because K is this commutator lambda A. And when you do the diagonal elements, it comes out like that. Lambda is diagonal, so each commutator gives you such a factor times A, so the double commutator gives you that. And interestingly, the diagonal elements are all 0 if you take J equal K. So you solve for AJK, you put it in Lagrangian, and you end up with this system. It's already looking suggestive, right? Because now you have this sum with these K's appearing here, and this Calogero type of denominator plus the potential. The only thing is that these K's are not a constant, they depend on the particles, and in general they are also time dependent. So if you go from the Lagrangian to Hamiltonian, the Hamiltonian would be something like that. The K's, as I said, are dynamical, and we are now facing the task of having to choose sectors for J and K. That means choose specific initial values for this conserved quantity. Clearly, if that initial value J, which is a constant, is 0, you can choose it to be 0, then K is 0, and you get free particles. This is the well-known fact that if you look at the sector of a model, of this model that is invariant under unitary rotations, that's what J equals 0 means, you get free particles. Where do you get the Calogero model that we know and like? You say, okay, so if J is 0, it's not interesting, it's free particles. I would like to make J non-zero and keep it as simple as possible. What's the simplest form of J that I can have if it's not 0? Because the trace of J is 0, J is a commutator, you cannot choose it to be proportional to the identity matrix, a constant. That would be the next best choice. So you say that the best you can do is to put it equal to a constant minus an operator of rank 1 that would subtract the trace. So you put it equal to L times VV dagger, which is the projection. V is any vector. So it's the projection on that one-dimensional space minus 1. And the length of V is n, or rather square root of n, such that the trace of this guy is 0. If you were to write it in a diagonal, it would be L, 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 and then the last element minus L minus 1, minus NL minus 1, something like that. Okay. Now, that's nice, because that tells us that K, which is J, but conjugated by this U, K is U minus 1 J U, can be expressed in terms of J itself. And the only thing that this U does is that it takes this vector U and it rotates it to a different vector U. So we started with this arbitrary constant vector U. Now we end up with this other vector U, which is in general time dependent. Because of the condition Ki equals 0, we realize that Ui star equals 1, because the diagonal elements here are Ui star minus 1. So without any sum, it tells you that the length of this vector must be 1. It can be time dependent, but it has to satisfy this condition. So the coefficient of the inverse square potential, which was Kij, Kji, if you remember it was here, if you express it in this form, it becomes L times this times L times that, but you see that you have UI star, UJ star. Each one of these terms is 1. So even if U is time dependent, there is no dependence here, and that turns out to be L squared. So lo and behold, you recover the Calogero model. So the Calogero model is embedded in the matrix model for this particular choice of that conserved quantity, that conserved momentum. You see that the strength of the model arose actually from the kinetic term of the matrix model and is related to that conserved charge J or L. The external potential can be arbitrary at this stage. I haven't talked about integrability. I just reduced the model to particles. And of course, other choices of this J are possible and correspondingly K, but we will postpone that discussion to the quantum case where things become more interesting. How can, yes? You generate integrable models where the particles also have internal degrees of freedom. Because these degrees of freedom that are now encoded by K, this K is a matrix that has its own dynamics, can be redistributed as degrees of freedom of particles. And I am going to talk about it, but directly in the quantum case where things are more interesting. Exactly. I would not call them time-dependent couplings. I would say dynamical couplings. The coupling becomes a dynamical variable that will depend on the spins of the particles, right? There is no explicit time dependence. It's a dynamical time dependence. Yes. Right. Yes, I flashed it, but before it was too brief. It is this, and it's a conserved quantity. That means J dot is 0. And that's a corollary of the fact that this initial action is invariant under time-independent unitary conjugations. If you take the time derivative, it will go here and here. When it goes here, it's identically 0. When it goes there, m double dot is proportional to the derivative of v, which is a function of m. M and n is scalar function of m commute, so this is constant. No, it does not mean that. It means that the matrix model has this invariance. How this invariance translates to integrability, you will see right now. So let's go to integrability. First, let's consider the free matrix model, no external potential. The matrix momentum m dot is trivially conserved. So the trace of its powers are also trivially constant. And because m dot is like a momentum, so if you were to endow the system with Poisson brackets, all the elements of m dot would correspond to momenta. All these quantities are Poisson trivial, they Poisson commute. So these quantities trivially Poisson commute among themselves. I2 is actually the Hamiltonian because its trace of m dot square is the kinetic term. So there you are. We proved integrability without even thinking about it as long as the potential is 0. If you wanted to express these quantities in terms of the traces of matrices, you could of course stick with the original matrix, but you could also do the unitary rotation that we did before. Remember, we defined matrix M as the diagonal plus U, so you can express it in terms of that U. You have M dot. It is the matrix L that we had before. We defined it before. It's matrix L, M dot in this representation. And when you write it out, the elements turn out to be like that. So it is something that should remind you of the Lux matrix that I wrote before, only here you still have a dynamical quantity Kij. But when, for the Ks that we considered before, for the J that we considered before in the corresponding case, this dynamical quantity turns out to be Uj, Uk star. This still doesn't look like a constant, but when you take the traces of these matrices, only products of that type appear where its index is paired with, its U with an index is paired with the same U with complex conjugate, and all these are equal to 1. So these terms will become constant, and actually, so that we get peace of mind, we can say we can take advantage of a residual symmetry that the system has, time-independent unitary transformations. You can always perform this extra unitary rotation, and by such unitary rotations, you can rotate all these U's to be equal to 1. You see, UI star should be 1, but UI could be a phase. You can eliminate these phases. So all these L's, all these I's here would, all these U's here would become a constant and equal to L. So this Lux matrix becomes identical to the Lux matrix that I showed before, which motivates why I wrote that form. Yes? Yes. So far, I'm talking about classical. So this is a classical matrix. We will quantize it. Numbers, but they are dynamical variables and they have Poisson brackets. Xi, pj equal delta ij, right? They're not operators. They will become the next, not the next slide. We can actually figure out the actual motion of the Calogero model. We can find how these particles will evolve. This picture that I showed you before, we can find it explicitly because the motion is free. So m dot is constant. So m has to be a matrix plus another matrix times time. That's the general solution. These two matrices have to satisfy the angular momentum constraint that this conserved quantity, which is that commutator, which is the commutator of these two constant matrices, has to have this form. So any choice of Hermitian matrices B and C that satisfy this constraint would give us a motion of this system. We have to identify such matrices satisfying this constraint written in terms of matrix elements in the cases where this UI is simply 1. And of course, you have various choices. One standard choice is what we call the initial value choice, in which we choose B to be diagonal. You can always choose one of them to be diagonal by global rotations. So if, where am I? So if B is diagonal, you write it as delta AK times some number Q. But then C cannot be diagonal. The diagonal elements are arbitrary, but the off-diagonal elements are fixed by this relation. And therefore, you write the solution as B plus this times time, so all this goes into the diagonal, and these multiplied by time remain in the off-diagonal. So this tells you that these P's are the initial values of the coordinates, and these P's are the initial values of the momenta. Why is that? If you put t equal to 0, m becomes b, so these diagonals become the coordinates. And if you ask what happens when you take a time derivative, the time derivative is just c. So, because this is multiplied by t, so at t equals 0, you would need to find the eigenvalues of this matrix, and they are exactly these diagonal elements. So that's why we call this parameterization the initial value. If you have the initial values q and p, you form these matrices, you write that time-dependent matrix, you diagonalize it. It's hard, but it's a completely algebraic task. There is your motion. And this also shows that this asymptotic momenta and impact, and what I call impact parameters, will be constant, because when time goes to infinity, then you see that all the off-diagonal terms will drop. And you can... What did I do? Oh, yes. I was pointing here while I should be pointing here. There is another choice for these matrices B and C that we call the scattering choice. It's when you choose C to be diagonal. So C is now a set of diagonal elements that I call K, and B is another set of arbitrary diagonal elements plus a fixed off-diagonal term, exactly the opposite as before. But now you see what happens, because this matrix C is multiplied by time t. At large times, the eigenvalues of M will be fixed by the eigenvalues of this matrix, plus the diagonal elements of this matrix. That's standard perturbation theory. The off-diagonal elements don't contribute. And therefore, at large times, the eigenvalues of M will be k times t plus a, and this will drop. So we proved the fact that asymptotically, these particles will move on straight lines with these quantities A being the same, either at time t plus infinity or minus infinity. So everything that I told you before is proven in this derivation. Yes, sir. For a particular... they are, because once you write the general solution here, you have to pick a gauge, a U. And these two gauges, that means choose one of them diagonal. It's the obvious choice to do to make things simple. Depending on which one you choose diagonal, you express it either in terms of initial value data or of scattering data. You could do other things, but they would give you the same solution. It may be. I never thought of it because it's not of any particular physical use, but it may be. Right. So when t is very large, you diagonalize ct plus b. You pull a t out, so you diagonalize c plus b over t. So you can do perturbation theory, because for large t this is infinitesimal. Standard perturbation theory tells you that the eigenvalues will be, of course, the large part, which is this, plus the diagonal of this, which is the standard perturbation theory, and the corrections come from second order perturbation theory. And that second order gives rise to these extra factors. So this is a standard perturbation in 1 over t. I didn't care to. And this is just to show you that these deviations of this parameter, of this impact parameters in time fall off as 1 over t, and also 1 over the relative momentum to the third. So if the relative momentum is large, they very quickly go to their initial values. If they are relatively close, they stay close for a long time. Right. We can now add a harmonic oscillator potential. The solutions, the matrix equations of motion are exactly the same as they would be for a particle undergoing harmonic oscillation. You can solve the system in exactly the same way as you would solve a classical harmonic oscillator. What do we do there? One way of doing it, which is nice because it makes contact with quantum mechanics, is that we define a complex quantity x dot p plus I omega x. So here the matrix m dot plus I omega m, omega being the frequency of the harmonic oscillator. That matrix evolves in this way, apply the equations of motion, and therefore, and the commutator of m and m dot becomes commutator of q and q dot, this constant, and therefore this q evolves trivially like that. You just solve this equation. So we have solved the system. This is the evolution of that matrix Q. Q of 0 is some non-Hermitian matrix, some non-Hermitian matrix that we can write as the Hermitian part and the anti-Hermitian part. These two, because of this condition, have to satisfy the same conditions as B and C before. That's why I gave them the same name. So everything you did before, you can redo it here. These B's and C's now are not initial values, but they parameterize the motion of the system. And conserved quantities, of course, are now arising out of taking Q dagger as an operator, in which case the time dependence drops. So Q dagger is time independent. The trace of any power of that will be time independent. So those are now the new conserved quantities for the harmonic Calogero model. The fact that these quantities are also in involution is not trivial anymore, because this Q contains both m and m dot, both coordinates and momenta, but it can still be proven by writing down the Poisson brackets of those Q's and working a little bit. So the harmonic Calogero model is again trivially solvable and integrable. And you can show, although it becomes quite a bit more complicated, that if you generalize this potential up to a quartic expression, you add m to the cube and m to the fourth terms for m, this full system, which is like an anharmonic oscillator trap with Calogero particles in it, is still integrable. And whether these are the only integrable models for the Calogero model on the line is actually an open question. I see that I'm going much slower than I had anticipated, so let's try to see. Okay, thank you. Let's go to the quantum Hermitian matrix model. Let's quantize this model. We have 3 minutes, so I think we can do it. First of all, quantizing this model at face value is again almost trivial, because look at it. I will write it, this is the Lagrangian of this model, I will write it in terms of the matrix element of M. So it's mij dot square minus omega square mij, or jk if you wish, squared. So this is actually the sum of n square independent harmonic oscillators. Each matrix element of M becomes a harmonic oscillator, or if you wish, the real and imaginary value, real and imaginary part of each matrix element become a harmonic oscillator. So n square harmonic oscillators, quantized, done. We did it. All the non-triviality in this is to re-express the quantization of this system in terms of the variables of interest, which are the eigenvalues. So all the interesting stuff is how do you relate those oscillators to the eigenvalues? Let's do that in a few steps. First of all, we define the canonical momentum matrix, which is m dot as before. We define the Hamiltonian like that. And now we quantize the system by promoting this matrix and its momentum into operators. The matrix and its momentum commute to the standard Poisson brackets, and this structure here tells you that M, the matrix element M and the matrix element of P commute in that form. There is a delta function between this index and that index, and the delta function between this index and that index. And here I will introduce a convenient notation. I will think of this matrix M as acting on space 1. So if you think of the matrix as an n by n operator, it acts on space 1. So these indices are on space 1. This matrix P acts on space 2. And this commutation relation now can be written as M1 P2, M acting on P2. The commutation, the quantum mechanical commutation between those two matrices is I T12, where T12 represents this element there. And this operator in the sense of matrices, that's why I was hesitating to use the word, but it's operator in the sense of acting as a matrix, is the operator that exchanges spaces 1 and 2. So if you commute this operator with a matrix acting on space 1, you get the same matrix acting on space 2. And also it's interesting that if you trace this operator with respect to any of the two spaces, if you trace, say, with respect to the indices J2, J2 here, you get the identity matrix in the remaining space. This, if you wish, I could have stayed with this index notation all the way, but it's so much more convenient that I decided to pay the price, introduce it here, and then use it. Now, motivated by what I did for the classical problem, I will define the corresponding ladder operators. They are the quantum versions of these Qs that I defined before. P plus I omega m and P minus I omega m, properly normalized as we do in quantum mechanics. Then, using the standard Poisson brackets for M and P, that means this Poisson quantum commutator for M and P, you can show that these two matrices, the elements of these two matrices, commute to T. So this is the corresponding, say that AA dagger commutator equal 1. Here it's not 1, but it is this T that permutes and joins these two spaces, while the matrix elements of A and of A dagger all commute. That's good, because now we can start trying to mimic what we know about oscillators using these matrix oscillator creation operators. We define these matrices L and R. L is exactly what you see, A dagger A, multiplied as matrices. R is this, which is A dagger, and then I have put this normal ordering. By that I mean the following. You multiply these two matrices as matrices in this order. You contract the indices as you would for two matrices in this order. But after you have done that and you have calculated the matrix element, each matrix element you reorder such that the momenta are to the right and the coordinates to the left. That's what this normal ordering means. I want to have all the p's, all the derivatives acting to the right and all the coordinates to the left. And those two are actually trivially related, because when you reorder it, you pick up just this extra term. These are now things that look like Hamiltonians, right? A dagger A is the harmonic oscillator Hamiltonian. Two versions of that Hamiltonian that are not equal, because you see that I multiply these matrices in different ways, so they are not equal in any exact sense. However, you can show that they satisfy these relations, which means that these creation operators act as creation operators for both of these matrices. R, because of this minus sign, there is a minus sign. And also you can find the quantum mechanical commutators of these L's, and they look like that. All this is a corollary of the fundamental commutator between M and P. And in this notation, they are very easy to find. So I stress that the algebra, quantum algebra of these L's is linear. It closes on L's. The same with R's, and they are identical. So this minus sign was crucial so that I get the same algebra, and that they mutually commute. So we have two copies of the same algebra for these operators L and R. What are these algebras? And I know that I'm going over time, so I will try to conclude somewhere here. What are these algebras? These are actually the UN algebras in disguise. These may not look like anything like the UN algebra. It doesn't contain any structure constants, but it is actually the UN algebra. The way to see it is to take this matrix L and decompose it in a complete set of n by n matrices, and such a basis can be chosen to be the fundamental generators of the UN algebra, the identity plus the SUN ones. So these expansion coefficients you call LA, these are not matrices anymore, but they are operators. Well, you write this, you know that these fundamental generators commute as matrices with the appropriate structure constants of UN or SUN. They obey that quantity. You substitute, you calculate the quantum commutators of LA and R, LA and LAP, LA and LB, and you substitute these expressions, and you use the quantum commutator for L and the matrix commutator for T, and lo and behold, you recover the standard SUN algebras. So this is a quantum UN algebra, two of them, one for L and one for R. This is a rather awkward moment to finish, but I believe that if I go any further, I will impose upon your patience. So we will leave it at that, and we will take it up tomorrow. We'll continue the quantization and move on to the unitary model and other hopefully interesting topics. All right.
Quantization for the external I was wondering about the quantization if the external potential is not quadratic but has a cubic and a quartic term.
It's not known, because even the scalar problem, a particle with cubic and quartic, is not exactly solvable. So clearly the corresponding matrix model is not solvable. All we know is that it is integrable, quantum mechanically integrable, but that's not enough to solve it.